This is not just steel and concrete rising out of a river. This is a $6.4 billion lifeline, physically forging two entire nations together. One cable, one pour, one impossibly precise mid-air connection at a time. What you're about to see is a pure engineering marvel, purpose-built to conquer a logistical nightmare that had been quietly strangling an entire continent's economy for more than half a century. And by the end of this story, you'll understand exactly why crews had to build North America's longest cable-stayed bridge to finally fix it. For over 50 years, one aging four-lane crossing carried nearly a quarter of all trade moving between the United States and Canada. A single narrow artery forced to handle the busiest international trade corridor on the entire continent, and it simply couldn't keep up anymore. The old bridge had reached its absolute limit, and everyone involved knew it. What they needed wasn't a patch, wasn't a quick fix. It was a solution built to last for the next 100 years, because every single hour of gridlock on that old crossing translated directly into billions of dollars in delayed trade, stalled supply chains, and mounting frustration on both sides of the border. This had become a crippling bottleneck demanding a genuinely monumental answer. And the answer that emerged wasn't simply a bigger bridge. It had to be smarter, structurally stronger, and visually iconic enough to represent the relationship between two entire countries. The audacious plan called for erecting a 6-lane, 2.5-kilometer suspended giant held aloft over the Detroit River by nothing but sheer engineering will, cable tension, and an almost unbelievable level of precision. This wasn't just about connecting two riverbanks. It was about connecting two countries, two border communities, and securing a trade lifeline that both economies had quietly depended on for generations without most people ever realizing just how fragile it actually was. The epic journey of this modern giant began about as humbly as any $6.4 billion megaproject possibly could, with a single scoop of earth turned over in early 2019 to eventually build a structure tall enough to scrape the clouds. Crews first had to dig deep, straight down into raw bedrock, moving over 1 million cubic meters of earth in total, enough excavated material to fill 400 full-sized Olympic swimming pools. Every single massive foundation supporting each of the bridge's two towers, each one roughly the height of a 75-story skyscraper, had to be flawlessly anchored into the unforgiving ground beneath the riverbank. Engineers needed to know the exact geological composition of the rock beneath them before they dared commit to a single design decision, because anchoring towers of this scale into unstable or poorly understood ground simply wasn't an option they could risk. To achieve that level of certainty, 6 enormous structural piles were violently drilled 36 meters straight down into the earth on each side of the river, forming the deep structural roots the entire bridge would eventually depend on. Inside those drilled shafts, massive rebar cages were lowered into place, forming an unyielding steel skeleton. But it was the continuous concrete pour that followed which delivered the foundation's true structural strength. Executing that critical foundation pour became a grueling, non-stop 24-hour marathon against the clock, because once a pour like this begins, it cannot simply be paused halfway through without compromising the entire structure. A staggering 2,000 cubic meters of heavy concrete were continuously poured just to form a single massive footing, an amount of material most construction crews would never handle in one uninterrupted session under any other circumstances. As that concrete cured, it generated significant internal heat, and engineers monitored it constantly around the clock, specifically to prevent any dangerous cracking from forming deep inside the mass before it fully hardened. Simultaneously, on the opposite bank of the river, an identical massive excavation and foundation process unfolded on the American side, mirroring every step happening in Canada almost exactly, coordinated across an international border in real time. With both foundations finally set and cured, the true race toward the sky could finally begin. To reach that height, the bridge's now iconic Y-shaped towers were built using an ingenious system of self-climbing hydraulic forms, a kind of mechanical formwork that literally jumped itself upward along the structure as each new section cured beneath it. Pour, let it set, jump the formwork upward, and repeat, over and over in a punishing but remarkably efficient cycle that continued for months. Every single rising segment of those towers became its own complex puzzle of dense steel reinforcement combined with highly specialized fast-curing concrete, engineered specifically to gain strength quickly enough to support the next segment being poured directly on top of it. At peak operational efficiency, crews managed to add another 4.5 vertical meters of finished concrete to the skyline roughly every 4 days, a pace that, for a structure this massive, borders on genuinely extraordinary. What you're actually looking at during this phase isn't simply concrete rising into the sky, it's the literal anchor points for the entire finished bridge, the exact locations where hundreds of steel cables would eventually be permanently tensioned. For several demanding months, the familiar skylines of two entirely different border cities, one in Canada, one in the United States, were visibly transformed by these two rapidly rising titans climbing toward the clouds on opposite sides of the water. While those massive towers continued reaching skyward, an entirely separate construction effort was quietly unfolding elsewhere, because the heavy steel bridge deck itself was being born inside an industrial fabrication facility, far from the riverbank. Every single piece of the eventual road deck was precision prefabricated off-site, to exacting engineering specifications long before it ever touched the actual bridge structure. These were genuinely gargantuan components, individual steel deck sections, weighing roughly 100 tons apiece, eventually destined to link together and form the bridge's 6 full lanes of continuous traffic. Safely transporting these colossal prefabricated steel segments from the fabrication yard to the active riverside construction site turned out to be an enormous logistical feat entirely on its own, one that demanded constant attention to wind conditions, river current, and road clearances, with literally every single move planned down to the inch well in advance. Finally, after months of preparation, the truly perilous moment of truth arrived. The delicate operation of flawlessly mating the very first heavy piece of prefabricated bridge deck directly to the tower itself. Engineers relied on massive strand jacks for this, essentially an enormously powerful winch system capable of slowly, precisely lifting a 100-ton steel segment straight up into position, using nothing but steel cable and controlled hydraulic tension. Suspended by what looked, from a distance, like impossibly thin threads of steel, that first 100-ton piece of future roadway began its excruciatingly slow, genuinely nerve-wracking vertical journey toward the tower high above the river. This ranked among the single most delicate operations of the entire project, because everything about the lift, the load, the angle, the tension across every cable had to remain perfectly balanced throughout the entire process. Down below on the ground, a tense team of engineers frantically monitored hundreds of live data points simultaneously, working to guarantee an absolutely level, perfectly controlled lift from beginning to end. When it finally reached its target position, the massive steel segment slid smoothly into a perfect flush fit. And just like that, the foundational first piece of this entire international crossing was securely locked into place. The instant that connection was made, crews immediately got to work permanently bolting the segment directly into the tower structure, using thousands of massive, high-strength industrial bolts, each one required to safely hold this critical mid-air connection securely together for at least the next 100 years. Heavy steel segment by heavy steel segment, the immense bridge slowly began its historic structural march outward, extending further and further across the open expanse of the Detroit River. As the deck continued growing outward from each tower, engineers relied on temporary support cables specifically to bear the weight of each newly installed segment until the permanent cable system could eventually take over that structural role entirely. For genuinely agonizing months, two enormous cantilevered steel arms reached blindly outward toward one another from opposite sides of the rushing river below, growing closer with every completed segment but still separated by open air and rushing water. However, the true structural magic behind any modern cable-stayed bridge doesn't actually live in the steel deck itself. It lives hidden within the breathtaking internal tension of the cables holding that deck aloft. Each individual cable wasn't simply one solid piece of steel. It was actually a tightly bundled collection of individual steel strands. Up to 131 high-tension strands per cable, each strand incredibly dense and just 7 millimeters thick, tightly bound together to form a single unified structural cable. These massive steel lifelines were precision, fabricated at a specialized factory located all the way in Italy, then carefully shipped thousands of miles across the ocean specifically to be installed on this one bridge. With both towers finally topped out at full height, it was finally time to begin installing the permanent cable system that would give the entire bridge its lasting structural integrity. Installing all 224 of the bridge's permanent, instantly recognizable yellow cables turned out to be an unforgiving process, demanding immense precision, alongside raw mechanical tension at every single step. Engineers would first run a lightweight pilot line across the necessary span, then use that thin pilot line to gradually pull the much heavier permanent cable up into its final position. Tethered securely to heavy industrial winches, the very first of the bridge's iconic yellow cables began its own remarkably slow, carefully monitored journey into its permanent position high above the river. One end of every cable was firmly anchored directly into the deck, while the opposite end was carefully lifted and secured into its designated anchor point high inside the tower itself. Once properly anchored deep within the tower structure, the genuinely dangerous hydraulic process of physically stressing each individual cable finally began, a process absolutely essential to giving the finished bridge its true structural strength. Engineers used specialized hydraulic jacks to stretch every single strand within each cable to a precise, carefully pre-calculated tension level, leaving zero room for error or approximation. Using truly immense hydraulic pressure, every single installed cable across the entire bridge was ultimately tensioned with well over 1,000 tons of pure, unyielding mechanical force. The moment the very first structural stay cable was fully and officially completed, it hung there as a striking visual signal of the incredible cumulative strength still to come as hundreds more cables followed behind it. As engineering teams continued adding cable after cable, the bridge gradually began supporting more and more of its own growing weight, which represented the entire key to the structure's evolving stability throughout construction. A genuinely beautiful harp of tensioned steel rapidly began emerging across the skyline, mathematically engineered from the very beginning to eventually carry the punishing daily load of millions of vehicles for decades into the future. This dizzying, highly technical installation process was perfectly mirrored simultaneously on both sides of the international border, creating what amounted to a breathtaking symphony of tightly coordinated engineering work unfolding across two entire countries at once. After years of mounting anticipation, the truly historic moment finally arrived. The spectacular high-altitude closure of the bridge's main span directly above the flowing river below. That final central steel closure segment had to achieve an almost microscopic, mathematically perfect fit, flawlessly accounting for temperature fluctuations, structural expansion, and the immense cumulative weight already bearing down on both cantilevered sections. Crews affectionately nicknamed it the Golden Bolt piece because this single massive steel segment represented the final structural key connecting two entirely sovereign nations together for the very first time. Decades of careful planning and years of genuinely backbreaking construction work all suddenly came down to this one single, unbelievably precise mid-air maneuver, executed with essentially no room whatsoever for error. In the exact fraction of a second that final gap was closed, the two separate, independently built cantilevers instantly became a single, unified, continuous structure. For the very first time in the history of this border crossing, a solid, unbroken ribbon of pure steel stretched proudly and continuously from Canada directly into the United States without a single visible seam. But a genuinely modern megabridge is always far more than simply a river span. It's an entire sprawling interconnected system. And at this stage, the work was still very far from finished. The new port of entry facility built alongside the bridge stands today as one of the largest standalone infrastructure projects in North America, entirely on its own merits. These absolutely cavernous new border processing facilities were custom designed from the ground up to simultaneously process over 10,000 heavy commercial trucks every single day, both safely and efficiently, without creating the exact kind of bottleneck this entire project had been built specifically to eliminate. Advanced scanning technology was integrated directly into the facility, specifically to help keep international trade moving both quickly and securely across the border. A deeply buried network of fiber optic data cables now forms the bridge's entire digital nervous system, silently and continuously, monitoring virtually every aspect of the structure's ongoing physical health in real time. With the massive steel structure of the bridge itself finally complete, engineering focus rapidly shifted toward creating the actual multi-lane driving surface that millions of future travelers would eventually experience firsthand. Thousands of heavy-duty shear studs were rapidly welded into position across the deck, permanently locking the eventual concrete road surface directly and securely to the bare steel structure beneath it. An intricate steel rebar web was then meticulously laid out across the entire length of the span, carefully preparing the bridge for its final critical layer of structural concrete. A truly gargantuan paving machine moved continuously across the deck, pouring, vibrating, and precisely smoothing the wide concrete roadway in one single, agonizingly slow, continuous pass from one end to the other. The specific surface texture applied here wasn't accidental. It was carefully engineered specifically for both vehicle traction and effective water drainage during heavy rain, an intentional part of the overall design rather than an afterthought. A literal river of freshly poured wet concrete relentlessly flowed forward across the deck, gradually transforming the raw steel skeleton beneath it into what would soon become a smooth, thoroughly modern highway surface. Once that concrete fully cured, crews could finally begin the essential final finishing work, starting with waterproofing. Thick layers of industrial waterproofing membrane were carefully burned directly into place across the deck, specifically designed to permanently protect the underlying steel and concrete from corrosive road salt and seasonal ice damage for decades to come. Finally, a thick, steaming top layer of high-friction asphalt was rolled out across the entire span, specifically engineered to provide a flawlessly smooth, safe ride for the millions of future travelers who would eventually cross this bridge. This surface represented exactly what people would actually drive on every single day. And it absolutely had to be perfect, with zero room for shortcuts anywhere along its length. Because safety at these heights was treated as an absolute, non-negotiable priority, heavy precast concrete median barriers were permanently installed specifically to physically separate opposing lanes of high-speed traffic from one another. Bright, highly reflective white lane markings were then carefully laid down across the dark. Fresh asphalt, instantly bringing the vast new highway surface to visible life with clear, rigid lane order. Massive overhead gantries were installed specifically to hold essential highway signage, lighting fixtures, and the bridge's intelligent transportation monitoring systems. High above the roadway itself, thousands of advanced LED lighting fixtures were carefully bolted into place, specifically engineered to illuminate the entire bridge deck, making the crossing both genuinely safer to drive at night and visually iconic from a distance. All of this critical environmental and structural monitoring data now feeds continuously into a dedicated central control room, allowing engineers complete, uninterrupted 24-hour monitoring of this newly completed structural titan. Under the glow of its own newly installed lighting system, the completed bridge finally took on its dramatic final visual form, shining as a genuinely brilliant beacon directly on the international border it now physically spans. And yet, remarkably, the main river span itself represented only a fraction of the overall story here. Several additional miles of elevated concrete approach bridges also had to be separately designed and constructed on both sides of the water. These extensive approach structures were specifically built to connect the bridge's dramatic main span directly to the surrounding customs plazas and existing local road networks on each side of the border. Down at ground level, final landscaping touches were carefully put into place across the completed site. Massive green highway directional signs were hoisted into position along the approach roads. This genuinely monumental megaproject was finally nearing its absolute finish line after several long, physically demanding years of essentially nonstop construction work. But before the bridge could ever open to the public, engineers first had to definitively prove the completed structure could actually handle its intended real-world load. Dozens of heavy dump trucks, each one precisely weighed and carefully loaded to exact specifications, were parked in calculated geometric patterns across the deck specifically to aggressively test the bridge's real structural response under significant weight. Engineers measured the resulting deflection of the entire bridge deck down to the individual millimeter, confirming that the structure was behaving exactly as originally designed, with zero unexpected structural surprises. Against a darkened night sky, the completed bridge put on a genuinely spectacular LED light show, serving as a brilliant final dress rehearsal ahead of its eventual grand public debut. Meanwhile, over on the American side of the river, the massive new port of Entry Plaza stood completely pristine and perfectly ready to begin processing inbound international traffic for the very first time. This facility was never intended to function like a simple, old-fashioned toll booth. It was designed from the ground up as a genuinely high-tech campus purpose-built for international trade and border security operations. Inside, hundreds of newly hired border staff underwent extensive training on state-of-the-art processing systems, preparing to operate what now stands as the most technologically advanced international crossing anywhere in North America. Crucially, the overall project also deliberately included expansive public park spaces along the surrounding riverbanks, specifically designed to connect local citizens directly to this landmark on the ground, just as meaningfully as the soaring economic connection it now represents high above them. Rising from raw, deep bedrock all the way up into the clouds, this entire structure gradually evolved from a single technical engineering drawing into a genuinely vital, beating continental link between two nations. Interestingly, even before the bridge officially opened to human traffic, local wildlife had already quietly begun calling parts of the structure home. For the thousands of dedicated ironworkers, engineers, and tradespeople who spent years of their lives on this project, this monumental undertaking clearly became far more than simply another job to clock in and out of. Inside the project's administrative buildings, the very last meticulous items on an exhaustive multi-year construction punch list were finally checked off one by one. Every remaining detail was carefully finalized to get this structure genuinely ready for its most important job of all, faithfully serving the public for generations to come. After years of deafening, non-stop heavy construction noise, the surrounding industrial soundscape abruptly, almost eerily, fell silent. Every single one of the bridge's highly tensioned cables was now performing flawlessly, permanently holding its precisely designated section of the massive roadway suspended securely high above the water. Engineers understand that any bridge of this colossal size is, in a very real sense, a genuinely living structure, meticulously designed with massive expansion joints specifically engineered to safely flex and move naturally along with the earth beneath it. The massive plaza complex surrounding the bridge also deliberately embraces the future of sustainable infrastructure, utilizing sprawling arrays of cutting-edge solar panels specifically to cleanly power much of its daily operational needs. Every single micro detail of this project, right down to the storm drainage system hidden deep within the concrete itself, was meticulously over-engineered from the very beginning, with absolute safety as the guiding priority. What finally emerged from all of this became a genuine symbol of two nations standing side by side, permanently connected by this single incredible structure. At long last, the mighty structural giant stood fully finished. The asphalt had fully cured, every cable sat perfectly taut, and the stage was finally set for an entirely new era of connection between two neighboring countries. For the very first time in this border crossing's entire history, pedestrians and cyclists would now be able to safely cross the international boundary, completely separated from roaring commercial vehicle traffic. The sprawling customs facilities were deliberately designed with massive floor-to-ceiling glass windows specifically to feel genuinely bright and welcoming, acting as a thoughtfully designed high-tech first impression for anyone entering a new country for the very first time. Dawn finally broke on the historic opening day. The early morning mist slowly cleared to reveal a genuinely staggering new architectural landmark, now standing as a powerful steel artery connecting an entire continent together. The ceremonial ribbon was finally cut, and cheering echoed proudly across the completed deck. What had once been a frustrating decades-long traffic gridlock was now, almost instantly, a brilliantly seamless, high-speed journey directly and efficiently connecting two massive, deeply intertwined national economies. Take a moment to actually sit with what a project like this really represents, because the individual numbers, $6.4 billion, 224 cables, 2 towers each, rivaling a 75-story skyscraper, tend to blur together unless you stop and picture the human reality behind them. Somewhere on that job site, on any given morning for years, there were iron workers climbing self-climbing formwork hundreds of feet above a rushing river, trusting harnesses, trusting welds, trusting the calculations of engineers they'd likely never personally meet, simply because the schedule demanded another 4.5 meters of tower every 4 days, rain or shine, winter or summer. There were surveyors on both riverbanks, checking measurements against each other constantly, because two towers rising independently from opposite sides of an international border cannot simply be built by feel. Every centimeter has to be verified, cross-checked and verified again, since the entire project only works if two cantilevered arms, reaching blindly toward each other across open water, end up meeting in exactly the right place, at exactly the right height, down to a tolerance most people would consider borderline unbelievable for a structure this size. Consider, too, the sheer coordination required to run what amounted to two nearly identical megaprojects, simultaneously, one in Canada, one in the United States, separated by an international border, and by two entirely different regulatory systems, two different workforces, two different supply chains, and yet somehow converging toward a single shared closure point suspended above the middle of the Detroit River. That kind of cross-border synchronization doesn't happen by accident. It requires constant communication, shared engineering standards, and an almost obsessive level of trust between teams who, in many cases, were separated by the very river they were racing to bridge. And then there's the cable system itself, arguably the most quietly astonishing part of the entire structure. 224 individual cables, each one a tightly bundled cluster of up to 131 high-tension steel strands, fabricated in ocean, away in Italy and shipped across the Atlantic specifically for this one bridge, because not every factory on Earth is capable of producing cable to this exact specification. Each cable, once installed, had to be tensioned individually in careful sequence, with over 1,000 tons of hydraulic force applied strand by strand, because tensioning them out of order, or even slightly off from the calculated sequence, could throw the entire deck's geometry out of alignment before construction ever reached the critical closure point. It's worth remembering, too, that a bridge like this isn't simply engineered to survive its opening day. It's engineered to survive 100 years of vehicles, 100 years of freezing Michigan winters, 100 years of thermal expansion and contraction, 100 years of wind loading off the Great Lakes, all while carrying the daily economic weight of two national economies that depend on this exact crossing, remaining open, reliable, and structurally sound decade after decade. That's why the expansion joints matter as much as the cables. That's why the waterproofing membrane matters as much as the towers themselves. Every layer of this structure, from the drilled bedrock foundations far below the riverbed to the LED lighting fixtures mounted high above the roadway, was designed with that same 100-year horizon in mind, not simply to open successfully, but to quietly, reliably outlast everyone who built it. And in the end, that's really the story underneath every statistic in this video. A bridge like this isn't just steel, concrete, and tensioned cable. It's thousands of individual decisions, made correctly, under enormous pressure, by people whose names will rarely appear on any plaque, coordinated across an international border in service of something far bigger than any single one of them, a permanent physical connection between two nations that will likely still be carrying trucks, families, and everyday travelers back and forth long after everyone who poured that first foundation has retired, moved on, or passed the story, down to whoever asks about it next. Even the port of entry facilities, so easy to overlook next to the drama of towers and cables, represent a genuinely staggering feat of coordinated planning in their own right. Entire campuses built from scratch specifically to process 10,000 commercial trucks a day without ever recreating the exact bottleneck this whole project was built to. Eliminate, complete with their own security systems, their own staff training programs, their own solar arrays, their own storm drainage networks, quietly engineered with the same obsessive attention to detail as the main span itself. Engineers frequently dream of building something genuinely capable of outlasting them entirely. This, quite simply, is that exact dream, finally and fully realized.